Alright, I solved this problem a while ago, so hopefully I remember all the details on how to do it. I actually did the last part recently, but anyways, so let's see here. First we want to show that B is an ideal in R. So let's see here. So for all B1, B2 in B and R in R, for closure under addition, so we also need for all x in M, b1 plus b2 applied to x. Well, because this is an R module, you can just bring it through, and it's just the sum of these things. So that's closure under addition, and so that means that b1 plus b2 is in B, and then we also want rb applied to x to also be an element of B, and so we just associativity here. That's not even really a necessary. This part's like super obvious. Okay, so that's multiplying on the left. So if you take any element of B, multiply on the left by R, you get an element. I think we are working in commutative rings in this chapter, in which case you don't need to check the next part, but just in case we're not, assuming that we're if we don't have commutativity or whatever, let's just do the other one. Let's do multiplication on the right. This is a little more, not that much more interesting. So M is a left R module, and so since R is in R, Rx is in M, and so then this is just an element of M, and we're applying some element of B to it, and so this is equal to 0. So hence, B is an ideal. Let's see here. Okay, so that's the first part. Okay, so now for the next part. Let's see here. I proved that to prove that this action on M, this action of R mod C on M gives us an R mod C module. I proved that the map is well defined, and then proved that it satisfies all of the properties. I really feel like there should be some easy way to conclude that this is going to be, that it's going to satisfy all the properties just from the fact that as an R module it satisfies all the property. But oh well, I'm going to do all the details because that's what I did when I wrote this problem, and I haven't thought about it since. So I'm going to give it a name, and we're only going to, I'm not sure if I'm going to use it that much. So we're going to let phi from R mod C cross M to M be given. C, of course, here is any ideal contained in B. I'm not going to write that out. Be given by phi of A plus C x. This is, of course, an additive. We're taking modulo with respect to the additive group. So this is going to be equal to ax, where the multiplication, there's a hair on my screen. The multiplication on the right-hand side of this equality is the action given by M as a left R module. So yeah, so that's a SMAP. So to prove that phi is well defined. I don't know if this is hyphenated or not, but whatever. Here, all my stuff is all. Let's see here. What do we need to do? Suppose A plus. So A and B in R are such that A plus C equals B plus C, i.e. A is equivalent to B mod C, i.e. A equals B plus little c1 for some little c1 in C, big C. So then what? Then AX is obviously just A plus C X. Here, yeah, that's, this is of course phi, but I don't need to write it out. But A is equal to B plus C, so B plus C, or B plus C1, so B1 plus C1, this, and then just by our definition, considering this thing as an element of R, we have that this is equal to B plus C1 applied to X, and of course this is a module. Do we know that this is a module yet? Yes, we do, because this multiplication is the R module structure for M, not the R mod C module structure, which we don't know is an R module C, is an R mod C module structure. Ugh, so many definitions. So, yeah, this is well defined because this multiplication right here is the action of R on M, which defines M as an R module. Okay, so we're good here. But this, of course, is just Bx, since C1 is in, because C1 is an element of big C, which is a subset of big B, which means that it gets killed. So I'm pretty sure B is the annihilator or something like that. I don't know. I haven't really internalized the definition of the annihilator and everything. And that's also, that comes in the next section from the section that this thing is on. So maybe this exercise is just preparing you for that. But anyways, so this is this. And there you go. And that's of course since C1 is in C subset of B. So phi is well defined. To prove phi defines phi makes M an R mod C module we have a bunch of computations. We have here, let's see here. I'm going to suppress the C, or I'm going to suppress the phi. So this multiplication is phi, and then this becomes, no. Yeah, a plus b x plus y. This becomes a x plus y, and of course this here, this is so let's say this is phi, and this M is a left R module, the action will be given by psi. So this one is phi here, and this one is actually psi. Ugh, my computer's already freaking out. This is my first video. So this is psi, and we know that psi is a module, so we can do that. And then this, we just convert it back to phi. So that's basically, I think that's the main idea of all of these things that we end up checking, is that we convert these statements about phi to statements about psi, and then use that psi as defines our module structure on M. Left R module, whatever. So there's that. Now if we have a plus b plus c applied to x, then this is of course a plus b applied to x. This is now c, and so because this is c, or psi, whatever it is, I'll call it c, or psi, I'll call it psi. It becomes this, and that is not right. It's this. And of course that is a plus cx plus b plus cx. Then ab plus c applied to x equals ab applied to x. And of course this, because this is multiplication with c, or psi, god, I keep forgetting. You just move it around. That becomes a plus c applied to bx. No. A plus c bx, which is a plus c applied to a plus b, no, b plus c x, I think. Right. So we have ab becomes a of b. So here we have the a times b here. So the a and b are at the beginning, so here it's like the a and the b are separated. So this notation might be a little confusing, but it works out. Whatever, however it works. Yeah, this is it. And then 1 plus c applied to x is 1x, which is equal to x, because that's how it works for c, or yeah, for c. What else? Oh, I guess there is nothing else. The last page was just me trying to figure out, or the next page was me trying to figure out where we use the fact that that C is a ideal contained in B, and I couldn't figure it out, and so then I kind of left this problem for like a couple weeks, I think, because I didn't know what to do. And then I realized, oh, because if it's not a subset of B, then you can't prove that it's well defined. Although I didn't fully think about that, or think about like, where's a counterexample where you have an ideal that is not contained in the annihilator, or whatever the set B is, and such that you can exhibit, you can look at the R mod C structure and show that this action does not define a module, like that you get some issue with the map. But I didn't really look into that. But yeah, this is everything that you need for this problem, and so there we go. We've done the proof.